Okay, welcome to example number 2. Very similar to the last question, except there's a few things added to here where we're going to talk about the photon rate at which photons are emitted per second. Okay, we have a typical laser pen that has a power of 3 milliwatts. I'm sure if you notice that says 3 milliwatts, hopefully you realize that's the power, which we'll probably want to convert that into watts. So that's 3 times 10 to the power of negative 3 watts. And hopefully you see that a watt is really an energy per unit time, so that's a joule per second. And this laser pen has a wavelength of 633 nanometers. Now, again, you could write this in terms of meters. It would be 633 times 10 to the power negative 9 meters. Or you may want to leave it in nanometers depending on which constants you tend to use. So in part A, we're asked to find out what is the frequency of the light that is emitted by this photon. Um, Thinking E equals HF, but I don't know the frequency, right? Oh, that's what we're looking for. Yes, we're looking, but we don't know the energy, so I can't really use that. Um, Oh, we do know that all photons travel at the speed of light. So we should write that down as given too. 3 times 10 to the power of 8 meters per second. And you can think of a photon as it is traveling through space like a wave. So you can use the wave equation, C equals F times lambda. So let's come back to that one in a minute. So we'll start out with C equals F times lambda, and we're going to be solving for the frequency of this photon, which would be the speed of light divided by the wavelength. So the speed of light is 3 times 10 to the power of 8 meters per second, which means that our wavelength must be in meters. You can't be using nanometers, you're not going to get your frequency in the right units. So we're going to have to write this as 633, but times 10 to the power of negative 9 meters. And you can see that the meters cancel out, and so I'll have 1 over seconds, which is really hertz. And this gives you a frequency of 4.74 times 10 to the power of 14 hertz. Okay, now let's go on to part B. What is the energy of the photon in terms of joules? So we go back to that equation that I actually wrote earlier. E equals H times F, because we now know the frequency. You could also use, or I suppose you could use E equals HC over lambda, because you also know the wavelength. So it's really up to you how you want to solve the problem. I'll stick with the first one that I've written down. Now, I want the energy in joules, so I need to make sure that I use the appropriate Planck's constant. I want the one that has joules in it. That's 6.626 times 10 to the power negative 34 in joules times seconds, and then multiply by my frequency, 4.74 times 10 to the power 14 hertz. Well, let's just write that as 1 over seconds. And that way you can see that the seconds here and the seconds here cancel out. And I end up with an energy of 3.14 times 10 to the power of negative 19 joules. You could also write this in terms of electron volts. It really didn't. Oh, actually, that's what we're doing in part C. Let's go ahead and do that. So we're going to convert this into electron volts. 3.14 times 10 to the power negative 19 joules. To convert from joules to electron volts, we're going to multiply by 1 electron volt on top and divide by what that is equal to in joules, which is 1.6 times 10 to the power negative 19 joules. Once again, you can see our units cancel out appropriately, so we'll have electron volts on top, and you'll get an answer of 1.96 electron volts. Lots of ways of getting this answer too. You could have went back and used E equals HF and just used the H value that involves electron volts times seconds. That's, I believe, 4.136 times 10 to the power negative 15 in electron volt seconds. It's up to you how you do it. All right, now moving on to part D, the momentum of this photon. Now, remember, you do not want to make the mistake and assume that this momentum has mass. You can't use m times v. And furthermore, you don't know what the mass is anyway. It's massless, right? So how do you find the momentum of something that is massless? Well, momentum of a photon is h over the wavelength. H is Planck's constant. So if we use Planck's constant, that is 6.626 times 10 to the power of negative 34 joules seconds, And then therefore we should be using a wavelength that is in meters. So we're going to be using 633 times 10 to the power of negative 9 in meters. And you're going to get a momentum of 1.05 times 10 to the power of negative 27 in joules seconds over meters. I suppose you could write it in terms of kilograms times meter per second, but that would be a little bit misleading because there's no mass, there's no rest mass. Okay, now we move on to part E, which is something new. We're trying to determine the photon rate. You can kind of think of this laser light as like a sort of a raindrop analogy, like it consists of a stream of photons, like little particles that are all in line, zinging along like this. And so, and each of these little particles have this amount of energy. So we're looking for what is the power of that, the number of photons that are being emitted. So, and this is probably related, as you can see, as the number of joules per second. So for a monochromatic, that's a single frequency laser light, and with n photons, the total energy of the light would be like taking the number of photons that you have multiplied by the energy of a single photon, which is h times f. So the power of this laser light would be, if you remember, power is work over time, or the energy of the laser light divided by the time, t. Or you could substitute in here n times hf, that's the total energy of all of the energy that's coming from the light, divided by the time. And now, what we're really looking for in this problem is the number of photons per second. So that's the number of n divided by t. So I'm just going to simply write this as r for like rate. And the rate would be equal to n over t. But if we were going to rearrange this, because in this problem we're given the power and then we have the hf as well, so we could rewrite this as power divided by h times f. So our power in this question is 3 times 10 to the power of negative 3 joules per second. And then our energy, hf, we've actually already calculated that earlier. That's the energy of one single photon. Let's make sure that we choose the right one. We don't want to use the one in electron volts because that we see joules up here. We need to use the one that's in joules. So that's 3.14 times 10 to the power of negative 19 joules. And so I'll get R will be equal to 9.55 times 10 to the power of 15. And this is the number of photons that are emitted per second. Obviously, that's a large amount of photons per second. No wonder we're aware that we can see photons. This form is not on the formula sheet, so I think that you really should just kind of understand it conceptually. You see, think of that power as the total amount of energy that you get per second. And then this energy you calculated in B was the energy of a single photon. So if you want to find the number of photons per second, you really need to take like that total energy, which is 0.003 joules per second, and divide by the energy per photon, which is 3.14 times 10 to the power of negative 19 joules. And you can see it like with units. The joules and joules cancel out, and you get something per second, which is photons per second. If you think of it conceptually, then you can come up with it. You don't necessarily need to use any formulas with this here. And thinking about this question too as well, think about a laser pen. If you change the wavelength, if you go to a shorter wavelength, it's a higher frequency, then what's that going to change? It's going to change the amount of energy per photon, the amount of energy you get per second, or for every single photon. What happens if you change the intensity of the light beam, the laser? You have a higher intensity. What's that going to change? Is that going to make the photon travel any faster? No, because they're all going to travel at the same speed of light. Does that mean that each photon will have more energy if it's the same laser, same wavelength? No, that's not going to change either. Does it mean the photons are like larger? No, no. It means that there are actually more photons per second. So when we talk about the intensity of a beam, we're really talking about photons per second. Okay, that's it for example 2.